just for the sake of trying to understand what the just-in-time compiler does for us, let's try turning it off. So I'm going to start by just turning it off for our JIT demo. And I will go into Edit Configurations, and I'm going to add an option called xint. This means do not use any optimizations. I just want the code exactly as I wrote it. Please don't try and make it better. So if I run this code, this time, JIT demo, we see that there is no change over time. It always takes somewhere around 100,000 to 200,000 nanoseconds to create our 1,000 linked lists. Now it fluctuates for reasons that I guess you can learn about in 61C or in an operating systems course, but turning off the just-in-time compiler has caused our code to take longer. Okay? Now we wouldn't want to do that in practice, but just to understand what's going on. So let's go back to our timing tests and see what happens. So if we now go into timing tests and we turn off the just-in-time compiler, again with xint, please don't do this and forget about it, because it'll make your code really slow. So we run the timing tests again, and we'll see that they're going to take a lot longer. Even 10,000 items is taking a long time to run. So I'm going to change the workload, because it's too heavy duty, to be only between 1,000 and 100,000 items. So now when we run merge sort, we see that sorting 1,000 items takes around 1 million character comparisons. That's normal. Doing 10,000 takes 13.8 million or so, and that's 1.48 seconds. And then lastly, when we get up to 100,000 items, which used to be easy, it now takes us 14 seconds. Now by contrast, if we go to MSD sort, we see that for 10,000 items, it's 0.77 seconds. And for 100,000 items, it's 7.88 seconds. So in other words, this time when we reran it, MSD sort was actually faster. Okay? So we rerun our experiment with no just-in-time compiler, and we see that MSD sort is now faster, okay? Which is what we predicted in the first place. So to summarize, basically, the results of this experiment now, with the just-in-time compiler disabled, I will observe that both sorts are far slower. It takes so much more time to sort. And now, as we expected, merge sort is slower than our MSD sort, though not by as much as we predicted. We thought it would be log base 2 times slower, but in this experiment, this data is a little different because I created it earlier. But we expected a pretty big difference. So log base 2 of 100,000, that's, let's see, we can go look it up real quick. Log base 2 of 100,000. We expected it to be around 16 times slower, but actually it's only maybe 2 or 3 times slower. Okay, so our analysis is more correct now, but still not. This is still not the right cost model exactly. And something it tells us, though, that I think is very interesting is that the just-in-time compiler was able to really leverage and optimize those compare to calls when we did merge sort. So both sorts got faster when we turned on the just-in-time compiler, but the impact on merge sort was much greater. And that makes some intuitive sense to me because comparing a bunch of like A's to another string that's a bunch of A's over and over, there's some redundancy, and presumably something in the just-in-time compiler was able to identify that and optimize. Okay, so essentially, without the just-in-time compiler, our prediction is more correct, so still off, and our sorts are much slower. Okay, so then basically, to go back to our original question, the whole thing we've been talking about is which one's better, MSD or merge sort? And what we just saw is that if the just-in-time compiler is enabled, merge sort is much faster if the strings are equal, but it'll be slower if the just-in-time compiler is disabled. Now, since the just-in-time compiler is usually on, I'd say merge sort is the better choice for this case. But equal strings is not the only case, right? I mean, you don't even do that all that often. Why are you going to be sorting a bunch of equal strings? So we might also consider almost equal strings, or randomized strings, or perhaps some real-world strings from a data set you care about. In those cases, we may get totally different results. The only thing we could do is run some experiments. And you can do that if you want. Just a reminder that you can run these same experiments and see what happens for different choices of string conditions, say random. Okay? Now, in real-world applications, often the answer is you don't really care. That merge sort versus MSD, maybe it's a factor of 2 or 3 or 4 slower, who knows, for a good implementation. And that constant factor isn't going to be such a big deal. You can just throw more computers at it if you need to. But if it's a performance critical thing where you really, really, really care about that constant factor, the answer is you do profiling. You run your code on real-world implementations and you see which is better. So then bottom line, I would just say this. Algorithms can be really hard to compare. If you have two algorithms with the same order of growth, trying to come up with some cost model is very difficult because the cost model, if you just pick one operation, it's probably not going to be good enough, as we just saw. And even if you pick a cost model that's pretty comprehensive, that counts all kinds of things, the just-in-time compiler is going to make your life even more complicated because who knows what's going to happen underneath the hood. It's below the level of abstraction, so being able to analyze the code theoretically is almost impossible. And there's always the chance that maybe some tiny tweak to your algorithm is going to make your algorithm much faster. So even if you decide today that quicksort is not quite as good as merge sort or whatever, it may be that you tweak the quicksort partitioning strategy and then suddenly, oh, actually it's way better. Okay? So this is a very tricky issue and something that is really an engineering challenge more than some kind of math challenge. Now, one quick note as we close out this segment of lecture. The just-in-time compiler, it is an amazingly complex and crazy piece of code. And if you find this stuff cool, like you want to know how does it work, it's approachable. It's also an active area that people are working on a lot. CS164 is sort of the first step, though this won't really be covered in there. And maybe try to get involved with compiler research or projects out there. It's pretty arcane stuff, but pretty cool. Now, one quick note that I think is cute is that the old JIT just-in-time compiler that Java uses, called C2, it's so complicated in the John Oosterhout sense that at this point, as far as I understand, it's actually being abandoned. And the quote I got from this article I found interesting is that C2 is giving diminishing returns over time, and nobody's really made any major changes to the just-in-time compiler. And they go on to say that the code has become so hard to maintain and extend, and nobody can even learn how it works. We're basically just going to start over and build a new thing that we think is better. So even in the real world, even with something as absolutely crazy important as the just-in-time compiler, people still do the thing where it's like, okay, well, let's throw away the old code and build the new one. All right, probably way more than you ever wanted or needed to know about the just-in-time compiler, but I think it's important to know that it exists, and it makes the analysis of code quite tricky when you're trying to say this algorithm is better than another.